Hello, my people. I hope we are doing well. We're going to go ahead and go over some transformations of the tangent and cotangent functions. Probably going to be tangent in this video and cotangent in the next. The first order of business, however, is actually constructing the tangent and cotangent graphs. We'll construct the tangent graph here, and then I'll do probably two transformations on tangent, and in the next video I will construct the cotangent parent function and do transformations, probably two transformations on cotangent. Okay, tangent, if we remember, is sine over cosine. Okay, now let's go ahead and, since it has something to do with the the quotient between these two, let's go ahead and graph both of these. Actually, let's make that pi and 3 pi over 2, negative pi over 2, negative pi, and negative 3 pi over 2. Let's go ahead and that'll be 1, that'll be 2. And we're basically just scaling it like we scaled on the sine and cosine graph originally. Now, when you're doing sine, remember that it winds up being, the parent function winds up looking a lot like this, and I'm not going to go through why. If you want to know why, then go look at that video. But we need to get these in there, because despite the fact that tangent is not officially a rational function, because rational functions are defined as one polynomial over another, a lot of the same principles still apply, because it's a fraction, okay? And fractions behave similarly, whether they have numbers in them, whether they have polynomials, or whether they have trig functions. Now let's go ahead and do the cosine as well. So, like I said in class, for those of you that weren't there, I'll go ahead and repeat myself. I thought about the possibility of actually having a lot of these graphs created before I turn on the video. But I'm hoping that just the few seconds that it takes me to construct these graphs will, and watching me do them over and over and over and over, will be of some benefit, because, as I am wont to say, repetition is pedagogically advantageous, which is a fancy way of saying it's good for learning, okay? Watching me do something over and over and over again, you doing something yourself over and over and over again, is a good way to burn it into your long-term memory. Now, cosine we're going to do in this orange. I like to use the green, but the green for some odd reason just does not show up as well on the video. So I will try and use the green sparingly, since these two show up a little bit better. Okay. Now, we need to ask ourselves, when is a fraction equal to 0? I'm going to go ahead and slide something under here, since I'm going to use a Sharpie real quick. A fraction is 0 when its numerator is 0. So tangent is 0 where sine is 0. Okay? And therefore, it's 0 here, it's 0 here, it's 0 here, 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 and here. Okay? Now, we also know that a fraction is undefined where its denominator is 0. So wherever cosine is 0, tangent has an asymptote. And unlike the rational functions that you've dealt with in the past, this actually has an infinite number of asymptotes because cosine has an infinite number of zeros, right? It has a zero every pi units, starting at pi over, oh gosh, I did scale that wrong, but whatever. I'll address the scale here in just a moment. Okay. I was correct at the beginning in terms of the scale. That's pi, that's 2 pi, and that's 3 pi. Sorry about that. I'm just trying to do too many things at once, as we teachers often do. Now those are the easy points, all right? Those are the ones like, where is the numerator equal to 0? Where is the denominator equal to 0? Those are the things that you started doing when you had a rational function, like an official rational function, right? Now the other points are a little bit more difficult, and in order to chat about those, we'll go ahead and we'll try and just kind of limit So what we're going to do is we're just going to talk about what goes on between these two asymptotes. And more specifically, right at the beginning, we're going to talk about what happens between that 0, okay, and that asymptote at pi over 2. Now, there are 3 things that we need to acknowledge about those two graphs within that span. First of all, they're both positive. So tangent will have a positive ratio because no matter what you're doing between 0 and pi over 2, both the numerator and denominator is going to be positive. The second thing that needs to be noted is that at one point they intersect. Now that is a fancy way of saying at one point they're equal. And that point, of course, is pi over 4 root 2 over 2. And we should remember that from our unit circle. So at pi over 4, you're going to have root 2 over 2 over root 2 over 2. So at pi over 4, where this meets, tangent is equal to 1. Now, what happens as I'm basically moving from 0 to pi over 2 is I have a numerator that is increasing in value, and I have a denominator that's decreasing in value, okay? Now, how do you make a fraction larger? Well, a fraction gets larger when you make its numerator larger or when you make its denominator smaller. Now, as I move from 0 to pi over 2, both of those things are going on, okay? So I'm going to start here. I'm going to come up through this point at pi over 2, 1, and then I'm going to run off to infinity, and it's going to hug this asymptote. And that's because sine, as long as you don't actually get to pi over 2, as long as you're just approaching it, sine is going to get really, 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 really close to 1, and cosine is going to get really, really, really close to 0. So cosine is going to take on values like 1/1000th, 1/1,000,000th, 1/1,000,000,000th, and on and on and on and on. If you get those infinitesimally small numbers in the denominator, it's going to make the overall value of the ratio very, very large, okay? And so what we get is we get something that looks like that, okay? Now, let's go ahead and let's look at this half right here, okay? Well, we have a little bit of a different situation right there, okay? There's no point of intersection, but we will note that at one point, negative pi over 4, while sine and cosine don't have exactly the same value, they have values that are of equal magnitude, right? Of equal absolute value. Basically how far they are away from 0. So you're going to have a denominator that's negative root 2 over 2, a numerator that's negative root 2 over 2, and a denominator that's positive root 2 over 2. So what we're going to have here at pi over 4, negative pi over 4, is negative 1. And despite the fact that you have a negative sign value here, and just imagine yourself going to the left here, you're going from the 0 toward the asymptote. As you push that way toward the asymptote, something very similar is going to be happening in this span between 0 and negative pi over 2 as happened over here. Okay? The only difference is sine is increasing in its magnitude. It's just increasing negatively towards -1. And so that's why you wind up having that. Okay. Now I'm going to go ahead and put that in green. I know it doesn't show up quite as well as the other two colors, but I think it'll help us out just a smidge right there. Okay, now let's move on to this right here. And let's more specifically do the right-hand portion of that interval. Well, that looks really similar to that. It just looks like it's basically the same thing mirrored over to be negative. Well, what's great there is you do have a value. Okay, you have both of them negative. You have a value where they intersect right here. Okay, and you see the fact that in the same way as before, the sign value is increasing in magnitude. And by increasing in magnitude, I mean its absolute value. It's going from 0 to -1. So the numerator is getting larger, negatively, of course, and the denominator is getting smaller negatively. But of course, the negative over the negative is going to turn it positive, and I know that here at 5 pi over 4, I get an output of 1. Okay. And since the same thing is going on, and a negative over a negative is the same as a positive over a positive, I have, remarkably, the same behavior here from pi to 5 pi over 4 as I do here from 0 to pi. Okay, well, let's look at the left side of this interval that runs from pi over 2 to pi. This looks remarkably similar to what happened over here. As you were pushing from 0 to -5 pi over 2, the only difference is that your numerator now is positive and your denominator is negative, but it's exactly the same shape, okay? It's exactly the same shape in terms of what's going on, and so again, you're going to get the same shape because tangent doesn't care if it's a positive over a negative or a negative over a positive. It's still going to be a negative. And you're going to get exactly the same shape. Now, the whole point of showing you this and emphasizing those facts is now we understand why tangent has a period of pi, or at least we understand it a little bit better, right? Because a ratio doesn't care whether it gets its positive value from a positive over a positive or a negative over a negative, and it doesn't care if it gets its negative value from a negative over a positive or a positive over a negative, you have the same values recurring, not every 2 pi, but every pi as you move forward. Now, that was a really belabored way of explaining why the tangent function has the shape that it has. But before we move on to a couple of transformations, I want to basically emphasize the fact that these points that we plotted, okay, these points are the ones that are going to be significant in terms of transformation, right? Those are the points that you're going to want to grab onto and move and shape, and then, of course, extrapolate from there according to the period where those points recur to the left and to the right. Now, and I think you'll understand a little bit more about what I'm talking about when we actually do this. Okay. Now, we're going to do two examples. I've tried to pick ones that were a little bit different from the ones we did in class. But they can't be too dissimilar, otherwise they're just unmanageable numbers that we're dealing with, right? And I'm not looking to punish you with unmanageable numbers, but I don't want to give you enough variety, right? So let's do 1/2 tangent of 2x minus pi over 2. Now, there are 3 transformations there, but the first thing that needs to happen, of course, is I need to factor that 2 out. Now, remember, be very careful, because when you pull a 2 out of something, remember, factoring is a form of division. And if you're going to pull a 2 out of pi over 2, you are actually dividing it by 2 and turning it into pi over 4. Now, when you're going fast on a test, it's really easy to kind of accidentally go the opposite way and accidentally have x minus pi here instead of x minus pi over 4. A good idea is always, at least in your head, to then redistribute across and ensure that you're actually going to get what you had originally, so that you have confirmed that you are indeed changing the form of the function, but not the value of it, right? So we understand now that we are going to move to the right, pi over 4. We are going to horizontally shrink by 1/2, and we're going to vertically shrink by 1/2, okay? Now, before we get started, let's go ahead and scale the graph, right? Now, when we deal with sine and cosine, we often scale the graph. Pi is right here, so 3 boxes to pi. But I know that pi over 4 is a much more important value than pi over 3 or pi over 6. So what we're going to do instead is we're going to make pi every 4 boxes, and that sort of redoing the scale is going to just help us out a little bit. Now, we can go ahead and do the usual y scale. That's not going to be too bad. I haven't moved up or moved down, so I don't have to worry about any sort of shift pushing significant points off of the Cartesian plane. And that's what I'm really worried about, okay? Now, let's go ahead and do the parent. I know that, and I'm going to do this, I'm going to try to do it real quick, okay? And what's great is when you scale like this, you sort of get used to the fact that there are basically 5 of the parent, okay? And you know that here's a 0, 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 right? Because that's where sine was 0. But you also know that at pi over 4, you have a value of 1. And of course, you know that it happens every pi units to the left and to the right. You also know that negative pi over 4, you're going to have negative 1. And that, of course, is true to every pi to the left and to the right of that middle period right there from negative pi over 2 to pi over 2. And so, you know, that didn't take us too long at all. And if you know the points, it actually shouldn't be labor intensive to recreate the parent function every time you go along. Now, what I'm going to do is I'm going to take these 3 points and we're going to basically concentrate on this as a representative period. We're going to transform this period, and then, based upon our information that we gained here, we're going to extrapolate from there. Now, let's take this origin point. We're going to move pi over 4 to the right. Then I'm going to horizontally shrink. Well, like I've said before, horizontal shrinks, or horizontal change in shape in general, happens with respect to that new 0 value, right? Your x is equal to c value, which in this case is x is equal to pi over 4. So when I shift to here, I'm actually, and that dotted line is not supposed to be an asymptote. That's sort of your new axis, right? And I've basically referred to the shifts as creating new axes or faux axes. And that's kind of a nice way to think about it. But I'll draw the asymptotes much darker than that so you can distinguish between the two. I just wanted to emphasize that when we move over here, that point is on the 0 value. And because it's on the 0 value, you don't shrink 0. You also don't shrink 0, right? So it's horizontally on the 0. It's vertically on the 0. You don't shrink 0. Boom. That's your point, okay? Let's go ahead and take this point right here. I'm going to move over pi over 4, but it is pi over 4 away from that axis, right? And therefore, when I shrink by 1/2, I go to here. Horizontally shrink, and 1 box becomes half a box. And then vertically shrink, and 4 boxes becomes 2 boxes, and boom. There is your point. Now let's take this point. We're going to move pi over 4 over, okay? And from the opposite side, that point is also pi over 4 away from my 0. I'm going to horizontally shrink it, I'm going to vertically shrink it, and it goes right there. Now, I recognize the fact that my period is always 2 pi, or pi over b, okay? Basically it's the original period over your b value. And the original period for tangent, of course, is pi. My b value was 2, and therefore my new period is pi over 2, which means that the fact that it moved over and then it squeezed in, you have, well, that didn't show up very well. But basically, you have skinnier periods, right? And that original period moved over and then squeezed in, okay? And then, of course, it also squeezed this way by a factor of 2, or 1/2, however you want to think about it. So it was divided by 2 or multiplied by 1/2. And basically, now I know if that is representative of what happens every pi over 2, then all I have to do is just replicate that shape, right? So really, all you have to do is just transform one period and then copy, 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 copy all the way across. And I'm not going to draw all of the periods, but I'm going to just draw a couple of them. This happens every pi over 2. This happens every pi over 2. This happens every pi over 2. And boom, boom, and on and on and on and on and on and on and on, right? And let me go ahead and just make it nice and colorful, so especially when I scan this so I can post it with the playlist, you get nice, pretty, colorful scans. And there we go. That is that function right there. All right, let's go ahead and do one more. We might get close to 30 minutes on this video, but c'est la vie. Alrighty. Y is equal to -2 tangent of x over 2 minus pi plus 1. Now, that's actually several transformations. Let's go ahead and factor out our b value. That's obviously the first thing that we want to do. Now remember, yet again, when I factor out, that is a form of division. And if I'm going to factor out a 1/2 from pi, I'm basically dividing it by that number, right? Okay, so what that means is this winds up being minus 2 pi. Okay, now I have 4 transformations. I'm going to move it to the right, 2 pi. I'm going to horizontally stretch by 2, right? Because compensating for the 1/2, your inputs need to be twice as large. Then the tangent happens, and then you're going to have an x-axis reflection. You're going to have a vertical stretch of 2, and then it's going to move up 1. Well, since you're going to have a vertical stretch and it's going to move up 1, let's be cognizant of that when we're dealing with the scale. Let's go ahead and make it, every box is equal to, every 2 boxes is equal to 1 unit. So it's going to be 1, 2, 3, 4, 5. So I've basically changed the scaling that I normally do along the y by a factor of 2. Now, it is, again, it's tangent, so I'm going to basically put pi every 4 boxes. because pi over 4 is a more significant value for me than any other. That, of course, means that the parent is going to look much like it usually does. I'm just going to have to make it a little more squat to accommodate the change in the vertical scaling that I've done. So still have the zeros, every pi unit starting with the origin. But then remember that pi over 4, this is pi over 4, 1, and that's negative pi over 4, negative 1. And I simply need to replicate it on every period for the parent. And let's sort of just give ourselves a nice, good idea of what the parent is on this scale so that we can appreciate the transformation that occurs when we actually do finish it here in just a moment. Okay. Now, like we're always going to do, we're going to take a representative point, we're going to move it, and then we're going to extrapolate from that point what it is that we need to do, okay? Now, if I'm going to move to the right 2 pi, I'm going to remember that this is now my x is equal to c. It's probably not a good idea to put a dashed line right there just because all the other dashed lines are asymptotes. So we'll just sort of do this. We'll just draw ourselves a little arrow down here to remind ourselves of this. So what I'm going to do is I'm going to take this point, I'm going to move it over 2 pi. That is the 0 point, so I don't do my horizontal stretch, right? I also don't do my x-axis reflection or vertical stretch because that is the y value of 0, too. And then I'm going to move up 1, and boom, okay? Now, if I'm going to horizontally stretch by 2, what that means is that my period, okay, is pi over 1/2, or now 2 pi. So I need to basically recreate this point every 2 pi. So here it is, and here it is. Alrighty, let's go ahead and take this as a representative point. I'm going to move it over 2 pi, and then I'm going to stretch it. Now remember, the 0 point is right here. It is one box away, and to double that, I'm just going to move it to here. Then I'm going to x-axis reflect it, stretch it by 2, and then move it up 1. And then I need to remember that happens every period, and in this case the period is 2 pi, so I'm going to go ahead and move over 2 pi, and I'm going to put it here, and I'm going to put it here. Alrighty, let's take this. We're going to move it over 2 pi, and then we're going to remember that the 0 point is right here. That point is pi over 4 away from this 0 point, so I'm going to stretch it by 2, then I'm going to x-axis reflect it, then I'm going to vertically stretch it by 2, and I'm going to move it down, and I'm going to move it up 1. So, boom. And then this point gets replicated here, and gets replicated here. Now remember that we also need to figure out where the asymptotes are. Well, the asymptotes, since of course this is your new y is equal to d, this is your new what would have been the axis of oscillation were it a sine or cosine. So it's basically your asymptote is going to be halfway between here. So if this is at 0 and this is at negative 2 pi, then your new asymptote is going to be here at pi. I'll go ahead and do it in a little darker. Boom, 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 boom. And of course it's going to happen over here at pi as well. And so we're just going to okay. And that is what our transformed graph looks like. And we ought to be able to visualize it when we go back and look at our original. So we're going to take this function, we're going to move it over 2 pi, we're going to stretch it, we're going to reflect it, vertically stretch it, and then move it up. Okay, so if you just kind of look at basically this red graph right here and imagine it flipping over, stretching and then moving up one, you're going to get this orange graph right here. Okay, well, I hope that that was helpful and a nice supplement to the classroom, to the class video. I'm going to go ahead and do pretty much the same thing when we get to cotangent, and I'm going to construct it, explain why it has the shape that it has, and then of course we will move on from there to do two transformations on the cotangent graph. Okay. If you have any questions, as always, please do shoot me an email or shoot me a message in Teams. Bye.